All right, Calc folks, back here with another lecture. Actually, I think it is probably going to be our last lecture in our study of at least vector value functions for the moment. I say that because what we're going to see come back in chapter 17 is some multivariable vector valued functions, right? If that doesn't sound a little intimidating, you've got an analysis on maybe the first half of that with vector valued functions. We're going to look at next chapter 15 and be introducing ourselves to multivariable functions. And we're going to then combine these ideas in the next section of material, right? Or, well, in chapter 17 material, I should say. Turn on my lights a little bit here so I'm not greening out so much as I gotta just watch my hands. That's what's greening me out there. What we have left to talk about are what are called the tangential and normal components of acceleration. Right? In the back in the section on motion in space, we were introduced to the tangential and normal components of acceleration, and what we basically said is that they are some constant values, right, that scale our unit tangent and unit normal vectors to a particular size, right? These being unit vectors, when they are multiplied by a constant, they are scaled by that constant value, right? The tangential components and normal components of acceleration play the role of scalar multiples, right, on t and n respectively, right, where when scaled to a particular size, the tangential and the normal, right, and then added together, what you obtain is this sum of these two scaled vectors, and that sum of these two scaled vectors is our description of acceleration that we saw back in motion, right? When we see a description of acceleration given to us by a vector valued function, that is actually a summation of two descriptions. A description of change in velocity that's due to a change in speed, and a description of change in velocity due to a change in direction, right? Highlighted by if I bring this up here, excuse me, highlighted by this summation seen here. All right, the A of t bar times t bar highlights the change in speed that a change in velocity might illustrate, and the normal component of acceleration times the principal unit normal vector will highlight the change in direction that a change in velocity might illustrate, right? And when we sum these two scaled vectors, scaled by these components of acceleration, we do end up with and sum them together, we end up with this description of our acceleration vector, all right? T bar and n bar are the unit tangent and principal unit normal vectors, respectively. And A of t bar and A of n bar are the tangential and normal components of acceleration, respectively. And that is all rather intuitive. All right? We do go on to note these components of acceleration describe the amount of change in velocity in the tangential direction, speed change, and the amount of change in velocity in the normal direction, the directional change. We might say here directional change in velocity change. Right? Let's say it that way. To calculate these components of acceleration, we have the following theorem. Here's the theorem we use to calculate. Actually, I should say the following definition. Right? Given R bar in n-dimensional space, a smooth parameterized curve where the first and second derivatives of that curve exist, right? The components of acceleration for the motion in R bar, or in that n-dimensional space, described by R bar, are given by the tangential component, a of t bar, where you can see its calculation is the dot product of the velocity with the acceleration vector divided by the magnitude of the velocity vector. And the normal component is given by a of n bar, a of little n bar, which is equal to the magnitude of the cross product of the velocity with the acceleration vector divided by the magnitude of the velocity vector. All right? These are two of my more favorite calculations for tangential and normal components of acceleration, and these are what I present here in the definition for their calculation. We're talking motion in space. So if we will have a description of velocity, we will have a description of acceleration, and we can put those together in dot product and cross product calculations to produce these values seen in these components of acceleration. All right. These components of acceleration are scalar values, right? So you'll notice here you are taking the scalar value for the dot product of v with a, right, with the velocity and acceleration vector, that is a scalar value, divided by this magnitude, which is scalar, right, which produces a scalar result for the tangential component. For the normal component, it is the scalar value given by the magnitude for the vector value found using the cross product of v bar and a, right, divided by the scalar value given by, the magnitude for the velocity vector. All right? This magnitude divided by this magnitude are two scalars, right, in a ratio, which will produce a scalar result. Excuse me. I'm talking all day. If we look at an example here, I went ahead and went with three-dimensional motion. We might consider the motion of an object in three-dimensional space described by the vector valued function r bar t equal to the cosine t, comma sine t, comma t. And hopefully you've done enough study to understand that this is a helix in our space that's spiraling around the z-axis. All right. And what we might consider finding are the tangential and normal components of acceleration for motion along this helix. All right. Well, that will require calculating our velocity and acceleration vectors. So for r bar t, our position vector, the velocity and acceleration vectors are found as follows, using first and second derivatives of r bar. All right. First derivative of r bar is negative sine t cosine t comma 1. Second derivative of r bar, or the first derivative of v, right, vector v, the velocity vector, is negative cosine t comma negative sine t comma 0. Where? Well, and then I add to that, so I get into, so if we cross these two vectors, all right, this would put us into this cross product, this determinant calculation, where the first component is going to be the first component is going to be cosine t minus negative sine t times 1, which is just positive sine t. The second component is going to be 1 times negative cosine t minus negative sine t times 0, which is just negative cosine t. And the third component is going to come from crossing negative sine t times negative sine t plus minus negative cosine t times cosine t, which would produce that Pythagorean identity sine squared t plus cosine squared t, which simplifies to the value of 1. All right? Here's our cross product of those two, the velocity with the acceleration vector. All right? And so if we look at the magnitude, right, applying the magnitude is going to come from the square root for the sum of the components squared. Sine squared t plus cosine squared t plus 1 squared. Well, the sine squared plus cosine squared t is going to be that Pythagorean identity again, which simplifies to 1. So really the magnitude of this cross product of the velocity with the acceleration vector here is the square root of 2. All right? That is going to become the numerator in our, normal component of acceleration. And if we look at the dot product of these two vectors, well, that is just, if you remember dot product, the first component times the first component plus the second component times the second component plus the third component times the third component, which is going to give you positive sine t cosine t plus negative sine t cosine t, which all simplifies to 0. Right? Well, plus 0, right? Which all simplifies to 0 in value. Right? So in terms of the tangential component of acceleration, its numerator is going to be the value 0, which, take note, as long as the denominator is 0, which it is, we see here, it's going to result in 0 here. So, since the magnitude of the velocity vector, if we take note of it, is also equal to the square root of 2, right? The tangential component of acceleration is actually given by this quantity here. It is the value of 0, the value given by the dot product divided by the square root of 2, 0 over the square root of 2, which does equal 0. And the normal component of acceleration is given by the magnitude of the cross product over the magnitude of our velocity vector, which is the square root of 2 over the square root of 2, which is equal to 1. And in comparison to each other, certainly there is more of the change in velocity along this curve due to change in direction than there is with respect to change in speed, and that can be seen by comparing those two constants and a sub n being larger than a sub t. Right? But furthermore, since a sub t is 0, that is highlighting that none of the change in velocity is due to a change in speed, and that all of our change in velocity must be strictly due to a change in direction. And that's the behavior you would see on a helix behaving in this manner. As we go up that helix, it doesn't change its speed. All of the velocity change is due to a change in direction. Right? That curvature around the z-axis. We're not going faster as we go up it. We're curving around it at the same rate in terms of speed, right? In terms of forward motion. All right? And we do make that final note here. All right? Note, since a of t bar is equal to 0, none of this change in velocity is due to a change in the object's speed, folks. So, having introduced the principal unit normal vector, we can go a little further into our understanding of acceleration, right? We can actually look at this summation, this summary of acceleration, right, a little bit further. And what we do take note of is that we are taking the tangential vector to our curve, right, scaling it by the tangential component of acceleration, adding that to the principal unit normal vector scaled by the normal component of acceleration, and adding those two orthogonal vectors together. And what we end up with is this description of acceleration. That would be the sum of these two scaled vectors. And that acceleration is going to summarize how much is happening in that tangential direction and how much is happening in that orthogonal direction. The change in the tangential direction is change in speed. The change in the orthogonal direction is change in direction, right? Is the a description of the velocity's change in terms of its change in direction. All right, folks. Another quick video here over the tangential and normal components of acceleration. A bit on their interpretation. A little further, we looked at some of this in motion also, and kind of formalized it here. And their calculation, right? Which does come from a little dot product and cross product calculations, folks. So you do want to become familiar with those calculations of vectors. All right, we see those come in handy in these calculations. With that said, I will end my video for here. I'll post this, and I do believe this will be the last video in our study here of vector-valued functions. What we are going to come back to in a couple weeks' time here, in about a week and a half's time, after our next test, is going to be the study of multivariable functions. All right, and we'll get into that after the next test. But the next couple of class periods is going to be focused in on, first of all, wrapping up this material, and then next week, at the beginning of the week, looking at reviewing for the test, taking any last questions, and then getting us ready for the test on Thursday. All right, like I said, you're going to take a portion of that in class, and there's going to be a portion that you work outside of class. All right, and I'll have that to you also, hopefully, by the end of this week. With that said, I'll end this video. See you in class, folks.